We face a whole bunch of challenges now in terms of doing conservation in this day and age. First and foremost, the threats are continuing to grow, right? Temporal scale, spatial scale, all that kind of stuff. Our funding continues to degrade. Outside of this current administration, just in general, our society is less interested in investing in things the way we were during the Cold War. And then increasingly we're seeing, not just with former Secretary Pruitt right here, who you see, who announced he was going to be resigning as of Monday, but for a whole variety of reasons, we are not as integrated as we could be to deal with these, in many cases, global scale problems. So one of the responses we can take is the power of these small robotic craft. They are very distributed, give us a lot of flexibility. They're relatively cheap. They're scalable. They really allow us to leverage open source material, and at the same time, that's sort of the small scale. At the larger scale, they allow us to do citizen science in ways and at scales we heretofore could not do. And then lastly, by taking an interdisciplinary approach, we can realize all kinds of cool stuff. So a lot of times in our research projects, we have people from the art department, and we have business folks, and we have a whole mix of people, and that, I would argue, that makes our research stronger and more valuable to the user. So I call what we do conservation mechatronics. So mechatronics is this emerging term for folks that a little bit of mechanical stuff, a little bit of electronics, a little bit of this and that. But to apply that in a management context or a conservation context, it's very much so the same idea as a makerspace, right? Which is really about speed, innovation, creativity, try new things. Let's experiment with this approach. Let's experiment with that approach. We are technology agnostic in our lab and our research groups. We're not wedded to fixed wings or multi-rotor or 3DR or DJI or whatever. It's driven by the question and whatever the best tool is to get us the best data to help our manager colleagues. I'd also say, though, that as we've talked about in some previous sessions here, there's a non-trivial bureaucracy that's sort of burbling up, right? It's been burbling up for some time. FAA, risk management, all this and that. And we've found it easier to attack that bureaucracy by coming from the education side first. And that there's a little bit less resistance to starting stuff as an educational endeavor. It might morph into a more traditional research endeavor, but at least you can put the crowbar into the door with education. Seems to be a helpful thing. And we do flying robots and swimming robots. I'll probably run out of time to talk about the swimming robots, but I just want to run through some quick examples here for you guys to illustrate the point that you can do wonderful conservation work, as we just saw from Alicia, with relatively basic instruments, just off-the-shelf flying stuff, and essentially having a camera in the air. Or you can do stuff that's much more complicated. And so you can do something, this is a 3DR iris with just an old GoPro. That can be the perfect tool to get your answer. Or you might have to bring along a whole mobile lab to places that are, in other countries and things like that to make your complicated stuff work. Both can be valuable. I just want to show you a couple examples here, starting from the simple, going to the complex. So this is some of our work in just south of New Orleans, where we're restoring bottomland hardwood forest swamp. And as part of this, every March we do vegetation surveys, woody vegetation surveys, and we just started experimenting with using, and part of that is to measure the height of the tree. Very complex. A lot of times the trees have strange morphologies. You can't see them from the ground, even if you have a fancy laser beam measure or that kind of stuff. So we've been experimenting with flying up our drones, hovering them at the top of the tree, and using the altimeter to measure the height of the tree. So very simple, nothing high tech. And just as we saw earlier, we've also been doing work in the Maui Channel, doing more traditional behavioral ecology. So this is work of my colleague Rachel Cartwright, who has a nonprofit and takes. We have a class that we take there every spring or winter. In this case, we're looking at humpback whales. It's very similar to the example we just heard. So we're looking at condition of the mom, and this was traditionally done from boats. Sort of difficult to see, going up and down, hard to get a good perspective, having to get a lot closer with the boats to get the visual observation. Now, in this case, this is just a phantom footage. You don't have to get as close. You actually get better, higher quality data, and we've been able to ask some questions that heretofore we've not been able to with the traditional research methods. And then there's the whole seeing surprising things or getting a sense of something we didn't even know was there. In this case, I have a couple examples from the Thomas Fire, which happened this past Christmas time in Ventura County, the largest fire in California state history so far. This is right behind the City Hall, what used to be the Mission San Buenaventura. And this is a forgotten wall that nobody had seen in 150 years. So this is part of the infrastructure that was put in the 1700s. This is an unmortared, non-mortared wall that people were just so overgrown with native vegetation that nobody knew about it. The fire exposed all this, so we went out and mapped it for, in this case, a botanical garden, and created high-resolution maps, orthomosaics of this location, so that in the springtime, or excuse me, the wintertime when it rained, when the mud would flow over that wall and hide it, we could come back this spring and in the summer and show the archaeologists exactly where, plus or minus a couple centimeters, where those stone walls were. So really cool looking at some of the human history of our part of the world. And then you guys have probably all seen these. This is one of our earlier first ones from several years ago. But this is just regular, this is using Pix 4D, but this is using no ground control points, nothing fancy, just a 20-minute flight at about 150 feet. And this is mapping a sea cliff in Santa Barbara, creating a structure from motion, a point cloud, re-stretching stuff over there. And now we actually can have much higher resolution with our better cameras, ground control points, etc. But even this very brief mapping effort, you can use it to start looking at bird nesting habitat and things like that, were we to do it the traditional way, would create much more disturbance of the nests. We'd be much more likely to attract predators and stuff, so it would take us longer time. A quick fly, boom, boom, and we can process the data back in the lab. And then we're doing risk analysis things like this. This is one of my students' project. We did a senior thesis looking at coastal bluff erosion in San Diego. This is near Camp Pendleton. And essentially flew this and created a three-dimensional map in the fall, and then repeated several times. This is the most recent one in spring, just a few months ago. And in this case, you saw a large block failure from this particular cliff. And so this information then goes to the city or the county and helps them understand the risk management proposition for different property owners around, in this case, coastal bluffs. Again, very simple. You don't need a whole lot of high-tech stuff. We're building the next generation of our LIDAR now on attaching some LIDARs to our drones that we're able to build for about $11,000, and you can do biomass estimates of vegetation, and these prices are coming down every day. So more and more tools. So in this case, this is again the Thomas Fire, and what we've mapped right here, this right here is Carpinteria State Beach, again a stitched together orthomosaic. This is the deposited waste from the Montecito mudslides. So this is one of their spoils places where they were sucking up the mud, dumping it on the beach, right onto one of our long-term monitoring sites. Thank you very much, County of Santa Barbara. So a quick drone flight here allowed us to very rapidly measure the footprint of the impact, and we're doing that for all kinds of other rapid response needs as well, including this. So in this case, this is Matilaha Dam, which is behind the city of Ventura. And this is, again, right after the fire. And so we're looking down at this dam that we're hoping to take down. It needs to go down. That's another conversation. But in this case, you're looking at the burned hillside. And so we could show this to the disaster folks, and they could get a better sense of the erosion potential. And we can do calculations of hillside erosion that would be more rapidly filling in that reservoir. Perfect use for a drone in and out. And then we have more sophisticated things, such as this. This is a recent grant we just got funded through the California Air Resources Board. And this is looking at, so here's the Thomas Fire. If you guys aren't from the area, you won't really make that much sense to you. But this is the red is the perimeter of the fire. And then all these black dots are existing oil seeps, naturally occurring oil seeps, or oil and gas wellheads. And thousands of seeps were exposed to the fire. And we have no idea how many are still burning. Many, many, many are still burning. Our first responders don't have the time or the resources to go and inventory these things. And as you can see from here, all the vegetation is burned away from it, so there's no immediate fire worry. To put out these fires, you do not use regular water. You need a crazy chemical mix. And so it's a non-trivial thing. So this funding is going to allow us to go and hunt down these things with a variety of sensors. So this is a ZenMu, so this is infrared and regular visual spectrum. And then we have a VOC sensor, so we can go on, we can map the the seeps either that are smoking like this, you can see visually, that you can see thermally, or in the case of the methane sensors, we can actually sniff out when they're in these deep, old, abandoned mine shafts that don't present heat on the surface. So all kinds of stuff like that. We do the same thing underwater, and I'll just suffice it to say, and I'll conclude by saying that all of these things work on the same principle. All of this data is collected with undergrads, and it's totally within their wheelhouse. They all have 107s, they all go through our training, and this is definitely the start of scuba or the start of flight is the only analogy. We're jumping forward our science in really, really cool ways, and would love to talk with you guys more.